Hello and welcome to another episode of Peep, where we talk about one specific proposal of Ethereum. I'm your host Pooja, and today's topic is EIP-2666. EIP-2666 is a standard track core EIP proposed in the month of May and is being discussed for the upcoming Network Upgrade Berlin. We are joined by Alex Vlasov, the author of the proposal, to understand what this is all about. Welcome, Alex. The floor is all yours.
Okay, thank you, Pooja. So we will jump directly to a small overview how precompiles work. It's essential to understand the essence of this heap itself. So precompiles were introduced at the beginning when it was necessary to offload computation of some specific functions which were just too expensive if one would express them in terms of EVM and like solidity contract, for example. Oh, that's why there are few precompiles right now. They are from address 1 to address 8, which execute some CPU intensive tasks. One interesting thing about them is there is no code under these addresses, but whatever you send as input when you perform a call or a static call in EVM is just directly fed into the native function. And this function is pure, so it means that there is no access to disk and there are no IO operations, which are quite expensive in Ethereum right now. So everything which is done is just some piece of memory is sent to the function as the input, and then this function performs some computations. Also, for each precompile, one has to come up with a formula how to measure the gas spent by this precompile, because it's no longer in EVM environment, so you cannot pay a single and well-determined gas per each kind of operation. So it's kind of initial point from where we start. And first it comes at if EIP-2666 is accepted, which reduces the price of performing a specific calls to precompiles, because those calls, as was mentioned, are quite cheap. They don't need to read anything from disk. So EIP-2046 proposes to reduce a call for this specific case. If let's say we limit address range for all precompiles from 1 to 1023, so it's like lowest 10 bits of the address space, then one would be paying much less to perform such static call. And as an example, we will get to concrete numbers later. Right now, performing SHA-256 function would cost roughly 70 gas for actually performing the computations of the precompile itself, but it would cost 700 gas to actually perform the call to this precompile. So for end user, it's tenfold overhead. But first we need to perform some adjustments that will actually kind of fix the pricing, because when recently, well, quite recently, there was a set of EIPs 1107 and 1108 accepted, which changed the gas cost of BN add and BN mule multiplication precompiles. When new costs were proposed, like an excessive cost of call was taken into account. So let's kind of make it in concrete numbers. If one would actually benchmark BN edition precompile in a set of major Ethereum clients, he would get the numbers that in the worst case, this function just takes something as the input, do all necessary computations, and returns the output, would cost around 350 gas in the worst case in the slowest client, but it's still fine. At the moment, user actually pays only 150 for this precompile, but user also pays 700 to actually perform a call to precompile. So it's 850, so it's safe in a sense that it's larger than actual time which is taken to execute. So it's larger than the pure execution cost in terms of gas. But if 2046 is accepted with a constant of, let's say, 40 or 100, then altogether user will pay only 190 gas, which is smaller than actually what he will have to pay for a pure execution of this precompile, which would, and this would introduce a DOS vector. So it's necessary to fix the prices in a sense that we should just make BN addition and BN multiplication costs to be what they are from benchmarks, and don't internally compensate for inefficiency of paying 700 gas for a call to the precompile, where the 700 is wasted, kind of. Yeah.
Am I understanding right if I'd say that the intrinsic cost that we see here, the 150 for add or the 6,000 for multiplication, isn't supposed to be representative of how much the actual precompile operation costs, but it sort of takes into account the cost of call and then offsets the intrinsic by that?
Well, I'm not the person who proposed 11 or 7 and 11 or 8. And maybe by the time when benchmarks were done, and maybe they were done on not on a full set of clients. So some clients actually fit into this 150 and 6,000. They do, but not all of them. And so for a slowest client, the safe value will be 350, which is larger, but still this discrepancy is kind of covered by 700. So those fixes are just kind of safe values. They will still benefit the user because at the end of the day, final amount of gas will be smaller. So it's kind of prevention of any DOS vector. And also client developers would not need to kind of immediately do optimizations to feed in 150 and 6,000 gas, but they will immediately feed in 350 and 6,000 and 300 gas. So maybe intrinsic cost was actually correct, but it was measured not on a full set of clients. Maybe just on two specific ones which actually do feed into these values. But before this, there was in general a sentiment that call to precompile, it never takes this much time to execute in Ethereum node. So there was a sentiment that this value is kind of wasted. So let's kind of compensate for this waste. So this part of the precompile is actually just get everything homogeneous. So it's 40 gas, which is, I mean, for EIP-2666, if it's actually 40 gas, which Ethereum client spends to do a static call to the precompile, it still needs some manipulations. Like you still have to copy some memory. Then let's say it's 40 gas, but we measured it properly this time. It's not at 700 as for calls to precompile to contracts which requires reading from disk, for example. Then we just measure everything correctly. This is the first part of this EIP. So we just set correct values and set safe values. It's not a huge change. It's like only a few constants. And then there is what can be considered as the second part of this EIP, which is repricing of hash functions. Well, it's repricing of hash functions because other precompiles which exist. One of those is modular exponentiation, which is repriced in a different EIP. So this precompile will be repriced. Another precompile on address equal to 1 is just a memory copy, which is well priced. So actually, after this EIP is accepted, like almost every precompile is repriced to properly reflect like how expensive it is. And by properly reflect, I mean like how much CPU time execution takes, and then so we transform CPU execution time to the gas and set this price for every precompile. So for hash functions,
is there an algorithm for determining gas price based off of CPU cycle?
It's well, in theory, one would be able to measure CPU cycles directly, but in practice, it's usually done that we take EC recover as the ground truth. So we assume that EC recover precompile is priced properly for 7,000 gas. Then on a local machine, one runs a benchmark for EC recover. And then one can derive actually from execution time of EC recover how much gas can kind of this specific machine produce per second. And this constant is enough to transform any other measured execution time for any other function into its gas price. And it is specific machine dependent. It will depend on CPU frequency largely. But if we assume that everything just depends linearly on CPU frequency, then this constant will be machine specific, but in general, gas value will be proper on every machine.
I see.
For these hash functions, those are more or less standard hash functions, how they do work is when you feed the input of some lengths into this hash function, internally, depending on specific one, they do some work which involves padding the input value with few extra bytes. And then hash function starts to take a block length from this padded input and starts to kind of mutate internal state to produce the output at the end of the day. So those functions, they depend not on the length of the input, but first of all on the padded length of the input, and then like how many chunks of specific lengths this padded input will take. As an example, here I didn't post specific formulas. They can be found in EIP itself, but just as an example, at the moment for all those hash functions, and few of those are precompiles like SHA-256 and RIPE-MD, and Kichak is actually EVM opcode, but it doesn't change in nature that any such operation has to be properly priced. Internally, those functions actually they depend differently on the input length, but here we only have examples. Right now, the pricing formulas are the same for all of those hash functions, in the sense that user pays some specific upfront amount, and then user pays for every 32 byte length of the input. In practice, if one would look at the internal structure of the hash functions or just perform benchmarking of these hash functions on different lengths of the input, starting from 0 bytes and doing steps like 1 byte each. After this benchmark, one would observe that execution time of these functions behaves like a step function and with steps at some specific values. So for example, Kichak-256 hash function will take the same time to execute if input is empty, so like 0 bytes, or if input is 128 bytes. The execution time will be the same, and it just reflects the internal structure of the hash function. For SHA-256, this is the same behavior, just constants will change. Here, for example, 0 bytes and 48 bytes still will be the same internal execution, still will be the same execution time, even while if we use existing formula for pricing, one would have to pay different prices for these two cases. And
then the 32 byte, the 32 bytes that you mentioned before, that steps on top of that, as in you have the minimum benchmark of either 128 or not benchmark, the minimum of 128 bytes for Ketchak or 48 for SHA. And then after that, it steps in 32 bytes. Am I understanding that right?
No, it's actually like, for example, I didn't want to place explicit formulas here, but for Ketchak, it's much simpler. It steps on 136 bytes only. So just in equal chunks. For SHA, it's a little bit different. You have the offset, but in general, you step every like 64 bytes, but with a small offset. So that's why, like, for a function, there is no difference in the execution time if you feed 0 bytes or 48 bytes. But for example, if you would feed 56 bytes to SHA-256, you would get a different execution time.
And you're saying that the repricing needs to happen because right now the repricing is already giving different price. Sorry, the old pricing is already giving a different price between 0 and 48 for SHA-256 or between 0 and 128 for Ketchak.
Yeah, I find it kind of that if function has some internal structure and this internal structure determines a logic, what is execution time depending on the length of the input, we should try to reflect this logic in pricing formulas. And the kind of the funny fact that in this case, some use cases will actually benefit from this repricing, because if one would do the binary Merkle tree, where you would do a lot of operations of hashing 64 bytes, then you would actually pay less than you would currently pay for Ketchak 256 function.
Does that automatically mean that it's a DOS vector?
No, it doesn't mean that it's DOS vector. Those numbers which are proposed, I mean, if you represent the internal structure of the function in your gas pricing formula, it's not a DOS vector as it is. You just need to place proper coefficients in a formula. And those coefficients are also determined from the benchmarks. So benchmarks were supplied by major clients. I ran Open Ethereum and gas benchmarks myself, and guys from Nethermind and Besu provided the benchmarks, which they did by themselves. It allowed to determine the constants which have to be used in these formulas for pricing. So that's why it's not a DOS vector. We still take into account a concrete and real performance of all major clients, well, with maybe exception for Besu, which have a work planned to optimize these functions. So they kind of expect to do it by the end of the year. And among benchmarks which are close together and well optimized, we just take the values from the slowest one and use them as safe values for everyone. It still doesn't change the fact that if one would compare old pricing formulas and new pricing formulas, then for for almost every value, you still would get 1.5 reduction of the price. And it's also not a DOS vector because clients can handle it. And this is compared to the slowest implementations between the clients. If one would actually do it based on a pair of the fastest one, then this discount will be even larger, much closer to 2. So at the end of the day, like anyone who would want to have hash functions in his application or smart contract will allow his users to pay less for it. I don't kind of directly touch here that Ketchak 256 is extensively used in many other applications, like determining the storage address when one performs a storage operation. It's a little bit different deal, and those operations are priced from other considerations. Here, this EIP is only about pure hashing of the input array of bytes.
Mm-hmm.
Does it answer your question, or you want some more qualification?
That absolutely answers my question. Thank you.
I see James has joined. James, if you want to say something, we have a small break in discussion.
I'm just getting caught up. But glad to have you, Alex.
Okay, so then we can continue to the current state. As we discussed during the previous few slides already, all major clients, they have provided the benchmarks for current implementations, which allow to derive pricing formulas. So it was possible to determine all the necessary constants in the pricing formulas. EIP-2666 was also benchmarked by all major clients. So it wasn't necessary directly for this EIP, but it was a byproduct. So now it's possible to determine a concrete value for 2046, which would ideally speed up its inclusion. So now it's kind of waiting for decision and a word from clients developers how fast it can be implemented. But in general, the structure of this EIP is much less complex than another EIP which we have discussed, which is 2537. So here one doesn't take any complex cryptography or functions which can be implemented different ways. Here one just have to follow the spec to implement formula how to derive gas cost from the input, from the length of the input. So it should be much easier for developers to implement, and if necessary, I can also provide them with some help. So as for presentations, that's all. If there are some questions, we can discuss them.
In the proposal, I have seen the mention of EIP-2565. So I'm curious to understand the relationship with that proposal with this one, like with EIP-2666.
I don't remember all the EIPs by numbers, but I assume this is repricing of ModExp. I mean, this EIP reprices, proposes to reprice a lot of precompiles, but not all of them. So what was necessary for ModExp repricing proposal is that it doesn't follow the same path as was discussed in relationship with 2046, so that they don't have any internal compensation for a high cost of the call and static call to precompiles at the moment. And as far as I'm aware, they don't do this, so they properly measure on the execution time of the ModExp, not the full EVM environment around it. So when it's accepted, it will not be necessary to do any other adjustments if it's accepted before or after 2046.
I'm curious what your experience was like going into this as you were thinking about proposing it, or and as you kind of went into the code base and were discovering some of these price mismatches and things. Like, what was that like? Was there things that went expected? Were there things that were unexpected?
Well, I mean, initially I was attracted to this because SHA-256 had a concrete price of something like 60 gas flat plus 12 per 32 bytes of the input. So let's say it's like 100 gas per some invocation. And simultaneously, I would have to pay 700 gas for a call. So it would kind of immediately bump the final cost from 100 to 800. So then there was a discussion of EIP-2666, where it was mentioned that first of all, the value for 2046 is not final and wasn't properly benchmarked. And then there was also concern that it would potentially introduce some DOS vectors if other precompiles are not well priced. So I just decided to quickly do this part. It's like, at least for Rust, Open Ethereum client, and for Go in Gas client, it wasn't very quick to do. And then just by looking at the plots of execution time versus length of the inputs, it was clear that formulas have to be made different to actually reflect the behavior. So first I looked at the formula and then looked at the source code of hash functions just to confirm that it kind of behaves in a way which I expect from the plots. So it's kind of all together. Was just first started from some inefficiency which I found.
And 2046 is the reducing the static calls cost?
Yeah, it was proposed by exec, but was kind of in a stash for quite some time.
Have we kind of summarized what the meaning of that is for people who are listening in the call? I don't want to go back to that. I think it'd be important kind of just to say that if we haven't.
Yeah, I mean, we discussed it as the course of discussion of this first slide, which is now on the screen.
Okay.
In the sense that, yeah, in the sense that DS precompile is just a pure function. So everything you need to do is just take some code, take some piece of memory, and do an execution. You don't have to pay for cost of performing disk lookup if you actually do the call to any of the real contracts, which takes some storage. So that's why you can have different values for these two different use cases.
Yeah, it makes static call makes calling all precompiles more expensive. Some of them are really cheap or should be really cheap, and so then become way too expensive just by having static call. So I remember when we were first starting about this, getting excited. We've had a lot of discussions about gas costs over the past year and a half, and this is just some history. Because Axik originally proposed that, I think we talked it before he proposed about it as well, and it's always been this matter of, yeah, we have inefficiently priced precompiles or opcodes in general, and opcodes are the stuff that if you're doing something on Ethereum and your gas is whatever amount, it's because opcodes are adding up to that gas. So any reduction or more accurate gas cost for an opcode really means a reduction, mostly at this point, because most of them are overpriced. With the caveat that storage is most likely going to be increased. So it isn't like it's a universal thing.
I also remember, I think also Axik has mentioned that like modular addition and multiplication opcodes are also not properly priced, but it was somewhere in one of the chats. So no one has making an EIP to fix it, and no one did the benchmarks. So there may be more inefficiencies out there, but each of those requires quite a lot of work because one has to do the benchmarks on all major clients. And sometimes it's easy if you're familiar with the language and the internal structure, and sometimes it's most likely quite impossible to get in. Ethereum client is already quite complex. The only thing
we've always wanted to do the changes. Problem is it's really boring to do the work, and it's difficult. It's not, I guess boring isn't the right word, but it's not very exciting to go and benchmark precompiles on four different clients in different languages, where there's a lot of other work that is going on and needs to be done, so that we haven't had anyone do it. So seeing you do this for the precompiles and the EIPs you've been working on has been really awesome. And I'm looking forward to all of these things rolling out.
Well, there is one thing that cannot be fixed by this EIP, is that Blake precompile is still going to be unusable, unfortunately.
Can you say that last part again?
I mean, even with all these changes and reduction of the static call cost to precompiles, there is one more precompile people don't usually talk about, which is Blake 2 compression function.
Mm-hmm.
Unfortunately, still going to be unusable, even with all these changes.
Yep. And the reason that is because it's priced to do. How can I explain this?
It's quite easy to explain. Like in most use cases, actual execution time of this precompile itself will be in a range of, let's say, 10 gas. But then you would immediately pay 40 on top of this just for a static call. And you would need to do much more than one call to this precompile to actually implement Blake 2 hash function. Because current precompile is only kind of one internal routine of this hash function, not the hash function itself.
So there's a number of rounds. Blake, in order to do its work, it goes a number of rounds, and there's a kind of minimum round, and you have to charge for gas for each of those rounds. You can't charge them more than one gas.
It's not like even if you would charge one gas for a Blake 2 compression function itself in a precompile, you will always pay 40 on top when you will just try to call it. So it's immediately increases the final cost of implementing Blake as, for example, as a Solidity contract, like tenfold compared to implementing it as a full precompile for a specific hash function. It's just how the hash function works internally, and because you have to call this round function many times, and every time you will still pay for 40 gas to call this function, even while the function takes even one gas. It's a crazy overhead.
Yeah. So if the ways to get around that would be if a precompile could do a fraction of a gas per call, and further reductions on the cost for static calls going down.
Well, only reduction of static call to something like 0 or maybe like 5 would potentially make it feasible enough to start thinking about it. But I think only the ultimate fix of actually introducing completely separate precompile flow for Blake hash functions is a way to go.
Okay, so there's still work to do, and this is kind of the beginning of optimizing prices, which is for the network means reduced costs for a lot of these functions.
Well, yeah, I mean, as you mentioned, it's not always directly reduction of the cost. It may be necessary to adjust prices up or down depending on specific operations. But in general, such work as kind of a maintenance plus cleaning up potential exploits for DOS everywhere where it's possible.
Yeah.
Yeah, and if it's a reduction, then it's a direct benefit for end user.
Yep. And the reason why there's like hesitation to do this immediately is the DOS vector or denial of service. If we price a precompile or an opcode or anything too low, and someone can call it enough to spam the network and do something bad. So that's in between. We want to get the prices right, and the amount of work needed to verify that there isn't going to be a problem with the clients is just a lot.
Yeah, it's taken quite some time to measure just the precompiles, so it will take even more to reprice everything. But like internally, I have an impression that most of the opcodes and all and other operations is well priced, so it will be just kind of cherry picking the changes. But still, to be sure, one would have to do it over kind of every possible opcode and in general operation.
Yeah, so like a comprehensive benchmarking for all of the opcodes and precompiles for all of the clients.
Well, for precompiles, it's not necessary. If you price old ones and do proper work on new ones, but for opcodes, it's a challenging task.
Cool. Alita, you said you had a question?
Yeah, so sorry, I'm just sort of jumping in here pretty late, so I'm sorry if this has already been asked, but while I've been researching like how the EVM works, I feel like, so are like, is there any way around having a really, frankly, complex system to monitor the work done by the precompiles, or have we considered doing something along the lines of like a sub EVM style, like assembly or WebAssembly setup that can monitor the actions in the same way that I guess that wouldn't really be a precompile, but if that makes sense, like, because at the end of the day, you're still making assembly calls or that sort of stuff, and so if we can have like a sub-assembly monitoring system, wouldn't that be able to sort of increase transparency, if that makes sense?
I cannot kind of immediately imagine what you would call as a monitor system, but just if one would imagine, for example, moving all the precompiles to eWASM and just kind of have a single piece of WASM code which is executed by some virtual machine, which ensures I think ensures no consensus divergences. It would just introduce inefficiencies. This is like having a low gas price for these operations was initially reason why precompiles were introduced. And the Kachak itself, for example, was even made into the opcode. Because those functions are very fast on the processor itself, even without any CPU-specific assembly. But when implemented, but when the same code is compiled in WASM, usually it's still 3 to 5 times penalty to execute the same code. Like as an example, I think a year ago, someone has compiled a very popular cryptographic library, the lib sodium. It's a C library. He compiled it to WASM and tried to run benchmarks on kind of some popular set of operations there and functions. And in general, the execution time was 3 to 5 times larger in WASM compared to the native code. Of course, one can try to optimize WASM virtual machine, but it's still like, but if one would optimize WASM virtual machine all the way down, it will become the native code. So one would have to compile down to it. It's kind of an overhead, which usually any abstraction would pay.
Yeah, and kind of a way to think about it is when I call an Ethereum call or send an Ethereum transaction, I'm really saying, hey, I want these instructions to be run. This program, these little bits of code need to be flipped around and done whatever, and then saved how I'm requesting. And the people who run that code at the end, so those get put around in transactions. And in the end, the miners or block producers in Q's world are running that code, and that has like them having their computer run that code takes a certain amount of time. And so the closer you get to purely how their computer is running the code, then the less and more accurate you are going to be with the time, and then the less time also it takes, and so you then can charge less for that time.
So I can understand that logic in terms of the optimizations of it, but I do know, or as I understand it, precompiles in general are a pretty contentious topic within the community because they it's just sort of, you know, opaque, or it's not really clear as to what exactly is happening, because if they're just running, you know, a random code, how do you know that they're running that one, which I think is what you guys were talking about. But
I think the hesitation is a little bit different than that, because you can verify what a precompile is doing. Where the worry is every precompile we add is technically a technical debt. It's a moving forward, we need to support this function. And that can like add complexity and stuff. So between those things.
And I think I did notice the complexity thing. I don't mean to interrupt, but I guess one thing. Sorry, I'm trying to click. You know what? Why don't you go ahead? I'm sorry, I lost my train.
Oh, that's good.
Kind of the best example here would be a difference, or being more precise, no difference between the Ketchup and SHA-256 in Ethereum, where Ketchup itself is an opcode, which kind of no one cares about, but it's still a very complex function under this opcode, while SHA-256 being precompile, and it's called with a different semantics. But I mean, hash functions inside of them are still very untrivial functions. The same goes for any cryptography, and we use it every day when one signs a Ethereum transaction. And I think all of the clients until recently, they used this same and single library to make signatures, which is a C library for SecP curve, which is used by Bitcoin and Ethereum. And this doesn't trouble anyone. The only trouble becomes when people started to want kind of independent implementations, which actually becomes a technical debt. If everyone would call the same C library, and it's 4 times smaller amount of code to maintain, or just like use a reference implementation, and everyone who would do optimizations on top of this would be able to write his own and ensure that it follows the spec. There is no consensus difference. But for most of the crypto, it's just a problem. If you have a mistake internally, you will immediately see the divergences.
My immediate takeaway is that having complex codes that are precompiles might be sort of like a short-term fix for a long-term problem. and that problem being the general computational overhead of the network. And so it might, I guess, is there any sort of solution to that potential problem of incorporating complex algorithms that will need to change, but using highly optimized simple programs, if that makes sense? Like using the opcodes, which is more or less what it's doing, but why don't we just do KiCat with the other opcodes, for example? I mean, I saw the performance overhead problem, but doesn't that kind of limit the scope of the Ethereum network?
But what you propose is what I think is the same as what people try to do with going completely to WASM. And the idea is that in Ethereum 2.0, precompiles would just become the WASM code. It is possible solution. It just gets all the way down to the question of whether one would want to pay for this 3 to 5-fold inefficiency or not. And in general, people don't want to pay this high factors for inefficiency.
Okay, thank you.
I mean, from technical perspective, it's possible to come up with some uniform solution, but it will be just kind of too expensive to be run on a global computer. And one would maybe propose to offset it with kind of increasing the gas limits 3-fold. Maybe a solution. It requires extra amount of work to find this answer.
One of the goals of having this call is to talk about the next steps. So talking about the next step for this particular proposal, I'm not sure if it is already accepted as EFI, because I see this in the GitHub itself. Has it been merged?
I mean, in principle, it's in a state that it can be merged. I just asked to incorporate a few additional suggested changes. There is also kind of proposal to logically split it to 5 separate EIPs for each individual repricing, which doesn't change the nature, just change the form. So that's also possible to do. But yeah, in general, it wasn't, I think, it wasn't discussed in a full scope on the call, in a sense that now benchmarks are complete. Benchmarks from some clients were only obtained around 2 weeks ago. So now it's in a complete form, and it can be actually made for discussion whether it's eligible for inclusion or not, and like when and how it can be included.
Right. And we have James on the call, which I hope he can let us know more about it. Like, is this proposal good enough to be discussed in next all coder meeting as an EFI, and when we can expect it on YOLO or something?
It's definitely at a point where it could go, where it could be proposed EFI. I don't know what the core devs would say, so I don't want to speak for them. I can see that this is something that people we've already talked about quite a bit as well, even more than some other EIPs that are in EFI. As far as YOLO, the new version of YOLO, I'm hoping that this makes it in. So that's something that's on the horizon. Mm-hmm. And then that's the YOLO v2 is the pre-step before Berlin. So I don't want to get anyone too hyped and excited about things getting Berlin yet, but getting things onto YOLO v2 is sort of the next step. This is one of the ones that are being considered.
Talking about Berlin here, just for a minute, I want to come back to the relationship that this proposal includes. Alex, is it okay to say that for this EIP-2666 to be getting into Berlin, EIP-2666 that we are talking today is going to support a few operation of 2046, and for 2666, to measure the implicit compensation pre-2046, it is important for the implementation of proposal 2656. So all these three are interrelated, and if we are talking about Berlin, we can hope to get all three on board together.
I think, I mean, you can place ModX pre-pricing separately. It's completely independent. But this EIP and 2046, those are related in the sense that if 2046 is accepted in its current form, ideally one would want to do kind of this first part of changes simultaneously. And if one does this first part, it's actually not a big difference to do both parts. It's not new code which has to introduce, it's just few formulas which has to be adjusted and new coefficients. And repricing of precompiles has happened in the past, so this mechanism is already supported by Ethereum clients. But ModX is completely independent. It can be accepted either before or after 2046. There is no dependency there.
Okay, I got it. So, wow, so much of work that comes along with a proposal. I think it's important for the community to understand running the Ethereum chain is no kidding. Developers are highly committed and put a lot of work into every proposal. Those who are new viewers and subscribers and have not watched our earlier episode on EIP-2537 in 5 slides with Alex Vlasov, I would highly recommend to go back to the playlist Peep and EIP and watch that episode, because that's a proposal also being considered for Berlin upgrade and would be helpful to know what new changes are being brought by Ethereum developers with the network upgrade. The link for that episode is available on the card on the top right of the screen. And apart from this, there are a few other ERCs that could be of interest, so check out the playlist. All the links from today's episode, including the EIP discussion forum, like Fellowship of Ethereum Magician, where active discussion happens for this particular proposal, EIP-2666, and the presentation with the guest contacts will be added in the description below. Implementation related links for reference material with raw data, input and benchmarking and precompile testing are available in the proposal itself. That's all about this particular proposal. Well, thank you, Alex, for joining, and everyone for tuning in today. Make sure to subscribe the Ethereum Cat Herders YouTube channel. And if you have any questions, suggestion on which proposal you would like to hear more, please leave a comment below and we will reach out to the author. So see you all with another proposal in Peep and EIP. Till then, stay safe. Thank you, everyone.
Thank you, Pooja. Thanks, Alex. This is awesome.
Goodbye.